I want to talk about a type of process called an irreversible process. Now, irreversible processes are things that happen in nature all the time. And I'm just going to give you a few different examples of what I mean by an irreversible process. So here's one right here. I've got an eyedropper. I've dropped some food coloring into a glass of clear, colorless water. The drop goes in. If I wait a long time, the food color spreads out throughout the glass, and we get water that's completely colored. If it's red food coloring, I'll have red water at the end of the day. That's an irreversible process. Once it happens, it doesn't go back. It does not reverse itself. There's no way to go from having a bunch of red Kool-Aid looking water and then having all of the dye molecules go back into one tiny little droplet. Doesn't happen. Never happens in the real world. That's an irreversible process because it only goes one way. You can't reverse the process. Another example. Here I have a bomb. My little Tom and Jerry cartoonish bomb. If I light my fuse, the bomb explodes. So it's common to see bomb fragments going out in all directions. However, there's very little chances that you would ever be able to reverse this process. Right? Doesn't matter how precise my bomb fragment projectile thrower is going to be. I can never start with a bunch of bomb fragments and then shoot them back into each other and form a bomb again. It just doesn't work. It's an irreversible process. It goes from left to right. It never goes from right to left. Similarly, I have some hot tea. Suppose my hot tea is in a room temperature environment. Well, it will give off some of its thermal energy to the room temperature environment so that it cools down and eventually it reaches room temperature. If that is the case, doesn't matter how long we wait, we will never see the reverse thing happening. Right? If I have a glass of cold room temperature tea, it doesn't spontaneously suck energy out of the atmosphere to become hot. That's something that never happens. This is an irreversible process as well. It goes from left to right, hot to cold, never goes in the opposite direction. Now, what is it that causes certain processes like these to be irreversible? Why can't I, if the laws of physics are reversible and symmetric, so that if I just changed all the velocities to be negative, the particles would move in the opposite direction. If that's okay, why can't I ever go from bomb fragments to bomb, or from spread out dye to a single droplet of dye? What's physically preventing me from doing that? So why are some processes irreversible if there's no physical laws preventing them from happening? So for example, take my bomb fragments. I have a bomb, the bomb explodes into a million pieces. In principle, all I have to do is just reverse the velocity of those pieces so that instead of going out, they're now coming in with the same velocity. And if we were to do that, all my pieces would come together and form the bomb again. We never actually see that happening. It doesn't violate any physics laws. All we're doing is flipping the signs of velocity. We're not violating Newton's laws or conservation of energy. But we still never see that happen. Why is it that there are some processes that are irreversible, even though they don't violate any fundamental physics laws? Well, the reason has to deal with the second law of thermodynamics. The second law of thermodynamics says this. It says that there's this quantity, this physical quantity that we call the entropy. I'll talk more about what entropy means in a minute. But the entropy always increases. Some physical quantity called the entropy always increases. To put that in, I think, a more understandable way, since entropy is kind of a nebulous concept, I would say the second law of thermodynamics really says this. So, i.e., probable things tend to happen. probable events are more probable than improbable events, by definition. And so you'd expect things that are probable to happen more often than things that aren't very probable. So going back to my bomb analogy, if I have a bomb that explodes, I'm not really tracking where the particles are going. I just know they're going boom, out somewhere, far off in the distance. However, if I want all of my particles to come back in to a single spot and form something in the shape of a bomb, that has to happen in a very particular way. And it's very unlikely that all of the particles are going to land exactly where they need to be. All of the different bomb fragments are going to end up exactly where they need to be at exactly the right time. It's very unlikely. So the same thing is true if we generally consider what we call entropy. Entropy just means that probable things tend to happen. And if I look at the statistics of what events are more likely, that is actually what's causing thermodynamics to happen in the way that it does. And it's what causes irreversible processes to be irreversible. What it means, it's not that they can't go back the other way, it simply means it's just incredibly, incredibly unlikely. Now you may have heard entropy referred to as the amount of disorder in a physical system, or the amount of disorder in the universe. And I don't like the word disorder. I think it's a bad word. I think it's very misleading. And the reason is, disorder is really in the eyes of the beholder. Right? So when I go home and I'm putting my physics books and papers and stuff away, I have a very peculiar order that I like them to be in. And to the untrained eye, it looks like it's a giant mess. In fact, to my wife's eye, it looks like it's a giant mess. So she'll usually go and try to clean things up. And I'm like, no! And the reason is because there's a certain order to that. Even though it appears disorder to most people, I know where everything is. So order and disorder, I don't like those words because they're not very meaningful. To give another example, let's give a more physicsy example. This is a nanoscale system that is, it's called a self-assembled monolayer. So say we have two molecules, I'll draw them as red and green molecules. And let's see, here's some red molecules, here are some green molecules. And I'm drawing them in a particular pattern right now. Drawing two red, then two green, then two red, then two green. And you can imagine that these are two types of molecules that are stuck on a surface. So the white is some surface, and I'm just looking at it from the side. It's like little molecule trees growing up from the ground of the surface. Now, we could draw that in a different way. Maybe I have a red molecule here, a green one here, maybe a bunch of green, maybe a red, maybe another red over here, maybe a green, another green, maybe a few more red. I could try to draw it as randomly as possible, as disorganized as possible. So here I have very clear order. Two red, two green, two red, two green, two red, two green. Here, not as much order. Red, a few green, maybe another red. Which of these has more disorder? Well, if you're looking at disorder, you'd probably say this one. Because to human eyes, that seems more disordered than this nice regular pattern. However, which system has more entropy? We can tell that because we have this rule that entropy always increases. So if I start the system in any of these two states, eventually it'll end up in the one that has more entropy. And it turns out, for this particular system, it always ends up like this. You get these stripes of green molecules separated by stripes of red molecules. Okay. Even though to the untrained eye, that looks more ordered than this mess of spaghetti string molecules over here. Okay. So what is entropy if it's not just disordered? Well, We said before that the second law of thermodynamics says that entropy is always increasing, and really that means that just means that probable things tend to happen. And what that's going to mean is that there's going to be it's going to be true that this state, which I told you is the one that's going to happen, the thing that looks ordered, is more probable than the state that looks disordered, where I don't have the regular pattern of red, green, red, green. So why is this more probable than that? Well, the likelihood of a state for any system just has to deal with how many different ways can I put the molecules, how many different ways can I arrange the molecules and atoms in that system. Assuming that, as long as we're not violating any fundamental physics laws, assuming that every configuration is equally likely, it should be true that this configuration, well, it should be true that the configuration with more possible steps is more likely. They're all equally likely. And this, let's say I have 99 ways of arranging this configuration, but only one way of arranging this configuration. Well, this one's going to be 99 times more likely. And in fact, that's what's happening here. So for this system of molecules, it turns out that by arranging the molecules in stripes, that then individual atoms can kind of flop around even more, so that they can move in and have more configurations than they could if I randomly arranged the molecules in a disordered mess. So entropy really has to deal with not disorder, but the number of ways that I can arrange all of the atoms and molecules in the system. And if you have a state where you have more ways of arranging those molecules and atoms, then that state is going to be more likely than a state that doesn't have very many ways of arranging the molecules and atoms. So we've said that the state that has the most entropy is the one that's the most probable. Entropy is always increasing, which means it's just going to the state that's the most probable state. And we said that the most probable state is the one that has the largest number of ways that I can arrange the molecules in that state. So it's going to be necessary, in order to figure out which state is more entropic, I can either just measure that experimentally and see which state I get, but we actually want to do this more mathematically. So we want to talk about how to count the number of states that a system can be in. And we're going to do this with a very simple example for now. Let's just say I take the room that we happen to be in, that you happen to be in, and we're going to make an imaginary line down the center of that room. I'm going to divide it into the left half of the room and the right half of the room, and we're going to count the number of molecules on each side of the room. So let's say I put 4 molecules in my room. Right? Well, how many different ways can I arrange that? Actually, let's even go simple. Let's start off with 2 molecules. So here's molecule 1, here's molecule 2. Right? How many different ways can I arrange those 2 molecules? Well, I could have, let's divide this into left and right. I could put molecule 1 and molecule 2 both on the left side. I can put molecule 1 and molecule 2 both on the right side. I could put molecule 1 on the left side, molecule 2 on the right side. Or I could put molecule 2 on the left side and molecule 1 on the right side. Now, if I look at the number of ways I can put all of the molecules on the left side, there's only one way. Only one way. I've got to put both molecules on that side. That's only one way I can do that. If I look at the number of ways that I can put a molecule on the left side and a molecule on the right side, you can see I have 2 ways. I've got 2 ways of putting molecules evenly distributed. So 50% of the time, I'm going to have a molecule on the left side and a molecule on the right side. Let's try doing our calculation again, but now let's put 4 molecules in there and see what's more probable. Okay, so I'm going to do my chart a little bit differently this time. I'll say this is where molecule 1 is, this is where molecule 2 is, this is where molecule 3 is, and that's where molecule 4 is. So I could start off with all my molecules on the left side. So 1 is left, 2 is left, 3 is left, 4 is left. They're all on the left side, so I would take 2 and 4, move them over to the left side of the room, so that everybody on the right side, everybody on the left side of the room has tons of pressure that's popping their ears. Everybody on the right side of the room is suffocating and dying because they don't have any air to breathe. Okay, well that's one way of arranging the molecules. Alternatively, I could put this on the left, this on the left, this on the left, and then that guy on the right. That's easy enough to do. I can do left, left, right, left. Yeah, left, left, right, left. I could do, I could put this guy. Right, left, left. I could put this guy. Right, left, left, left. Okay, so just looking here, there's only one way that I can put all of the molecules on the left side of the room. But I have 4 ways of putting 3 molecules on the left side of the room and 1 molecule on the right side of the room. And this will be a general trend. So the closer you get to 50-50, half of the molecules on the left, half of the molecules on the right, the more probable it's going to get. So I have one way of putting them all on the left, I'll have one way of putting them all on the right. I'll have 4 ways of putting all but one of the molecules on the left. I'll have 4 ways of putting all but one of the molecules on the right. So far, that's 1 plus 4 plus 4 plus 1, which gives me 10 total ways of doing that. If you work out the math, you'll find out, let's see, 4 has 2 options, 3 has 2 options, left or right. 2 has 2 options, 1 has 2 options, always left or right. Which means there's 4 to the 2 to the 4 ways of looking at, 2 to the 4 method, try that one more time. There are 2 to the 4 ways I can arrange molecules on the left or right side of the room, which means 2 to the 4 is 16. So in total, there is 16 possibilities. If I tried to do my entire list, all the way down to everything on the right side of the room, I would get 16 possibilities, and it turns out that leaves 6 possibilities, or 6 ways, to get half on left and the other half on the right. I'm not going to go through the math. I trust that you can work that out on your own. And we're not going to do this for any more particles. We're going to stop at 4 because the number of ways goes up and up and up very, very quickly. So it would take a long time. But once you get to a mole of particles, typically what we have in a room this size, what you find is that pretty much everything is right around the 50-50 mark with very little fluctuation. So in a room this size, where we have 6.022 times 10 to the 23rd gas molecules, more or less, you're almost going to be spot on 50-50. Now, is there any, is the reason for this because there's some little demon that goes around trying to disorder things and increase the entropy? No, it's just statistically more likely. Because if you actually count the number of ways of arranging the molecules on the left side of the room and the right side of the room, it is much more likely, vastly more likely, that you're going to get 50-50 on either side than you are to get any huge deviation from that. So having 75% of your molecules on one side of the room, very, very, very unlikely. So we've talked about how to count the number of ways of arranging molecules in a room. For real-world systems, this gets more complicated because you've got to consider configurations that might have different energies. So we're not going to deal with that just now. However, I do want to give you a formal definition of the entropy, because we haven't actually said how the number of ways of arranging the molecules is at all related to the entropy of the system. So we're going to define our entropy in this way. So entropy gets the symbol S, and entropy is going to be equal to a constant, Boltzmann's constant, which you should have seen before, times the log, natural log, that's our natural log, of omega. Omega is the number of states the system can be in. System. Number of states the system can be in. So for example, suppose I wanted to know the entropy of the state where half of the molecules were on the left and half of the molecules were on the right. Well, I would look over here. I would look at how many molecules are there where half are on the left and half are on the right. Well, there's 6 ways I can do that. So I would say that the entropy is Kb times the log of 6 ways. Kb times the log of 6. Suppose I wanted to know what the entropy of having of a state where all my molecules are on the left side of the room is. Well, there's only one way to do that. So my entropy would be Kb, Boltzmann's constant, times the log of omega, where omega now is 1, because there's only one way of arranging the system where all the molecules are on the left side of the room. What's the log of 1? Well, just remember that log, when I take the log, well, really what I'm saying is e to what power is 1. The only way e is going to be equal 1 is if I take it to the power of 0. So the entropy for this system would be 0. Okay? So if I know all the molecules are on the left side of the room, there's only one way to get that. That gives you no entropy.